going to start kind of a new topic today that we'll look at in a couple of different ways over the next week or so, um, and that's the topic of what's called a differential equation. So, okay, so a differential equation. Oops, oops. Is going to be one that involves some unknown function y, possibly also, you know, the variable that it depends on, like x or t or something, but that it also involves derivatives of y. Okay, so some examples would be something like that, or something like that. Okay, so here I have an unknown function, y, and I want to figure out what it is, knowing that its derivative is equal to zero, or its second derivative is equal to zero, or um, that it is its own derivative. Okay, so all of these are examples of differential equations. These are pretty simple ones. And then the biggest derivative that appears in it, we classify these things based on that. So this one is first order, and so is this one. This one is called second order. Okay, so if the second derivative appears, it's second order. If the third derivative, it's third order, and so on. Okay, um, and let's say that both the first and the second derivative appear. This is still second order. So it's the highest derivative that appears that determines what its order is. Okay, now I will say that the topic of differential equations is gigantic. Okay, so much so that there are in fact multiple different courses that you could take that are on nothing but differential equations, right? So this is a very, very large topic in mathematics, um, and the the reason that it's so large is because there's a wide variety of different kinds of differential equations, and part of one of those courses is to classify the different kinds and then try to understand, okay, how could you identify what kind of differential equation is, and what techniques for solving it would be good, right? So there's a huge variety of those things. So we're going to look at some very simple ones, okay? Um, and in particular, one category that we're going to look at are ones that are called separable. Okay, and these are ones where you can get it to be y prime equals some function of t. Okay, so for example, y prime equals 2. That's separable. Okay, we're able to get the unknown derivative here and everything on the other side purely in terms of variables. And these are one of the easiest categories to solve because they just involve finding antiderivatives. Okay, so for example, if I said that y prime is equal to 2, what's the solution to this? Oops. Y prime would be 2t or 2x, just whatever the variable is, plus some unknown constant. Okay, um, because what's the derivative of 2t plus c? 2, which is what we started with. So it satisfies the given original equation. Okay, so this, when we get a solution like this, this is what's called a general solution because it still has this unknown constant in it, okay? And I don't know what that constant is. It could be anything. It could be a boat. No. From Family Guy when, Peter he wins the boat or the mystery box and he chooses the box because there could be anything in it. It could be even a boat. And Lois is like, Peter? Yeah. No. Huh? Absolutely nothing. Right. Yeah. And then the guy who, gave him the choice was like, "You're so stupid." So, yeah, anyway. And then the next scene, like you see all of his friends driving boats down towing boats behind their trucks down the street. So, yeah. Okay, so that constant could be anything. Okay, and I can't determine the constant unless I know one other piece of information. Okay, so we can determine if we know an initial condition. Okay, so for this example, let's just say something of this form. Y of 0 equals 7. And I'm just making up the numbers here. Okay, so what does y of 0 equals 7 mean? It, well, in this case, yeah, it would mean c is 7. But the statement y of 0 equals 7 says if you plug 0 in for t, then what y value should come out? 7. Okay, so if I do that, and I substitute t equals 0 and y equals 7 into my general solution, then I'm left with an equation that involves a bunch of numbers and c, and therefore what is c? In this case, it's 7 on the nose. Okay, so my specific solution is y equals 2t plus 7. Okay, so general solution still has a plus c, or unknown constant, or actually there could be multiple unknown constants. We'll look at an example of that. And then a specific solution is where you figured out what those unknown constants are. Okay, and you need at least one initial condition. You need one initial condition for every constant that you have. Okay, so a problem. Okay, is called an initial value problem. Okay, so this is something where you have a differential equation and some initial conditions, and the goal is to determine the function that satisfies all of that stuff. Okay, and like you said, there's going to be an art form to it. Okay, so any questions on that so far? Okay, now I should say solving initial value problem is tricky. Okay, if I give you what I claim is a solution, how could you check whether or not I'm correct or not? That's much simpler. Okay, so let's look at an example of that. Okay, so example, let's suppose that I have the differential equation that y prime minus 2, oops, sorry, that should be a minus, not a equals, minus 2y over t equals t cubed. Okay, so that's a differential equation. I don't necessarily know how to solve it, but suppose like somebody walks up on the street and they open up their trench coat and they say, I got your solution right here. Okay. And they claim that the following one of these might be a solution. Okay. Now, where did those come from? Right now, just think they came from the dude with the trench coat. Okay. But how would I check whether or not, like, what else do dudes in trench coats sell? Yeah, fake Rolexes, right? If any of you guys in the before times, did you ever travel and, you'd be in like Paris or something or New York and they're like, yeah, you want to buy a Rolex? It's just $10. Yeah, right. Like those are all fake, 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 fake. Okay. But they're fake, but how do you know they're fake? Well, there's that, right? Okay. But uh if you really wanted to know that they were fake, you'd have to like sit there and examine them and really kind of think it through. So here I have two things that are purported to be solutions to this differential equation. How can I check whether or not they actually are? Yeah. So I have the equation y prime minus 2y over t equals t cubed. Well, if I take the derivative of each of them and plug them into that equation and simplify and stuff, if I get t cubed out the other end, then what does that tell me? That it is a solution. Okay, and if I do that and I don't get t cubed, then what do I know then? It's a fake Rolex. Okay, so what's the derivative of each of these two functions? What's the derivative of the first one? 3t squared plus minus, right? 3 over t squared. And what about the second one? Yeah? Okay. So now substitute each of those into the given differential equation. So uh, 3t squared minus 3 over t squared minus 2 times t cubed plus 3 over t all over t. What is this equal to? Well, ugh, what do we get? 3t squared minus 3 over t squared minus 2t squared minus 6 over t squared. I think that's right. Do you guys agree with me? It's not t cubed. That's the worst looking. Let's try that again. That's definitely not equal to t cubed. Okay, so that's definitely a fake Rolex. All right, let's try the other one. Sorry. So what was the other one? It was 2t cubed plus 3t minus 2, uh, yeah, 2 times the solution, which was this. Oops, that should be a 2. T squared all over t. Okay, so let's simplify this guy. What do we got? 2t cubed plus 3t. The 2's cancel, t4, so that'd be minus t cubed. And then we'd have minus 3t cubed. Did I get, no, not t cubed, it'd just be t, because I haven't had coffee yet this morning, guys, so not really firing on all 4 cylinders. Okay, so what do we get here? T cubed. So that one's not the fake Rolex. Okay, so this is how you double check whether or not a solution that you've produced or somebody has produced for you is legit or not. Okay, you just plug it in, crunch it, do all the appropriate arithmetic and algebra and calculus, and then see what you get. Okay? All right, so does that make sense? So having that to check your work is certainly helpful. Okay, so um, let's flip over to the second page, okay? And let's start with the equation y prime equals sine of 2x. Okay, so this differential equation is not only separable, but it is already separated. Okay, meaning what's on the left? Y prime, and that's it. What's on the right? Are there anything involving y over there? No. Okay, so if it's in this form, basically all we have to do is find an antiderivative. Okay, so what's an antiderivative of sine? What function has sine as its derivative? Negative cosine, right? So you have to think backwards here. Okay, so claim, oops. All right, negative cosine of, do I need anything else there, Jaden? Okay, do I need anything else there, Jaden? Yeah, okay. So I claim that this is the appropriate antiderivative that we need. Okay, now you look at that and you say, where the hell did the 1/2 come from? Okay, it came from the chain rule, or sort of me thinking 2 steps ahead to know that I need to undo the chain rule. Okay, so what's the derivative of negative 1/2 cosine of 2x? Yeah, I'd have to say, well, what's the derivative of negative cosine? Sine, so I'm going to get sine of 2x with the 1/2 out front times what? The derivative of 2x, which is 2. Okay, so why did I have to multiply by that 2? Because of the chain rule. Okay, so I put the 1/2 in front of my answer, knowing that if I took the derivative, I would get a factor of 2. And how do I guarantee that those are going to cancel? By having a 2 to go with the half, right? Okay, so do you guys buy that the derivative of this is in fact sine of 2x? Okay, so now let's think about the thought process that went through my mind, okay, as to how I was able to start with sine of 2x and produce negative 1/2 cosine of 2x. Okay, so let's start with the first question I asked, which is what function has sine of x as its derivative? And you guys said, well, minus cos x does, right? So that told me I definitely needed a minus and I definitely needed a cos of something, okay? But did we have cos x or sine x here? No, we had sine 2x, okay? So let's say you just guessed that, minus cos of 2x. What would you get for your derivative? 2 sine of 2x, which is twice as big as what it was supposed to be. Okay, so if your answer is twice as big as what it's supposed to be, what does that tell you about your original solution? Yeah, multiply by half to fix that problem. Okay, so you see kind of how we have to do some backwards thinking here in order to deal with the chain rule issue. Okay. Now, I should say here, and this is really critical, you can only do that kind of backwards thinking if the chain rule would give you a constant. Okay, so what's the derivative of 2x? 2. Okay, let's say that the thing on the inside were x squared. And you'd say, oh, well, then there's going to be a 2x that I have to multiply by, so I'll divide by a 2x instead. No, absolutely not. It doesn't work that way. And we'll see examples of that later. Okay, so you can only kind of play that gambit if it's a constant that you're off by. If it's something involving a variable, you're hosed for now. Okay, and we'll look at how you get unhosed later. Okay? Okay, so now, does that work? Does this function satisfy the given differential equation? Yes, check. Okay, is this a general solution or a specific solution? Yeah, it's general. Okay, sometimes for specific we also say particular. That you see both words out there. Okay, it's general because do I have any way to determine this unknown constant? Nope, because I didn't give you any initial conditions. Okay. All right, so does that kind of make sense? Okay, so let's look at here another example. Okay, again, this one's separated, okay, because I've got all the variable stuff on one side and y prime on the other. Okay, so all I have to do is find an antiderivative. All right, so what's the antiderivative of 4 over 1 plus t squared? And if any of you say logarithm, I'm going to get my stick and beat you over the head. Because what should it be? No, we're not taking the derivative of it. We're taking the antiderivative. Right? What function has derivative 1 over 1 plus t squared? Almost. Arctangent of t. Okay, right? You fool, you fell for one of the classic blunders. Okay, so do you guys remember what's the derivative of arctangent of t? 1 over 1 plus t squared? Yeah? Well, you remember it now. Okay, and then there's that 4 out front, so he just hangs around. All right, what about the sine part? What function has sine as its derivative? Negative cosine, so we actually just did that. So it would be minus 3 cos of t plus an unknown constant. Okay. Okay, so does that thing have the appropriate derivative? Yes. Right. So this is the good thing about antiderivative problems. How can you check whether or not your answer is correct? If you take the derivative of your answer, what should you get? What you started with. Okay, and if you don't, that means you done screwed up, son. Okay. Yes? Excellent. Okay. Right. All right, so let's look at one that's maybe a little bit more spicy. Let's get up to like Buffalo, like Nashville hot kind of territory. How's that sound? All right, so let's try and solve the differential equation. Okay, the initial value problem equal to this. Okay, so two things are different. Do we have an initial value in this case? Yes, okay. So we got extra information, and that will allow us to determine the unknown constant once we get to that point. But we also have the differential equation, and is this separated? But is it separable? Yes, okay. How do I separate it? I just got to divide both sides by x, okay? Now, in doing so, I do have to be a little bit careful here because in the original differential equation, is x equal to 0 a valid thing? In the original equation, is x equals 0 okay? Yeah, because what's multiplying by 0 do? Okay, no big deal there. And also, what would square root of 0 be? Is that a problem? No, it's 0, okay? Whereas if I do the following, okay, Now, is x equals 0 valid? No. Okay, so I have kind of actually changed the domain a little bit here. Okay, which does bear some, some worry, and we'll see what happens when we look at this. Okay, so, and I'm sorry, that exponent is kind of unreadable. Okay, so that's y prime. What would y be? I need an antiderivative of this thing. Well, what's the antiderivative of 1 over x? Ln x. Okay, now, strictly speaking, there should be an absolute value there. Okay, but I'm going to remove the absolute value for technical reasons in this particular case. Okay, and the reason that I know I can do that is, let's look back to the original differential equation. Are negative values of x's valid? No, because I've got a square root. Okay, so if only positive x's are valid, do I need an absolute value? No, because what's the absolute value of a positive? Just itself. Okay, so I already know that I'm not working with negative x's, and so in general, I need that absolute value, but in this case, I can get away without it. Okay, so that's that first part. What about the other guy? What's the antiderivative of 2x to the minus a half? All right, here we got to be a little, let's do some thinking. So what's the power rule say for derivatives? You bring the exponent down and then subtract 1 from the exponent. Okay, that's the power rule for derivatives. So what's the opposite of doing that? Okay, almost. Okay, so let me change the question. All right, and I'm going to change the question to something that's going to seem absurd, but I promise it will make sense why. Okay, so how did I put my shoes on this morning? Well, all right, let's look. What do I got on? Yeah, I do have on some Asics. Okay, they're pretty nice, right? But I'm not just wearing Asics. I've also got some socks, right? So how did I put my shoes on this morning? I put the socks on first. Okay, so I put the socks on, and then I put my shoes on. Well, they were already untied because I had untied them yesterday when I took off the socks and shoes, right? Okay, so I walk into my living room. I have my socks on already. There are the shoes. I sit down, I put them on my feet and tie them, and off I go. Okay? All right, so when I get home tonight, how am I going to undo that process? Not only do I have to reverse each step, but I have to reverse the order in which I do the steps, right? So I put on my socks first, and then I put on my shoes. Okay? Well, what's the opposite of putting on shoes? Taking off shoes. What's the opposite of putting on socks? Taking off socks. Okay, but is it going to work particularly well if I try and take my socks off before I've removed my shoes? No, that's not going to work. Okay, so I have to reverse the steps, but also reverse the order of the steps. Okay, so I need to take the shoes off. That's the opposite of putting the shoes on, and it's also now the first step instead of the second step. Okay, so do you guys see what happens? Not only do each individual step flip, but the order in which I did them flipped. Okay, so what does this have to do with calculus? Let's go back to the power rule. If the power rule says step 1, multiply by the exponent, step 2, take 1 away from the exponent. What's the opposite of taking 1 away from the exponent? Adding 1 to the exponent. What's the opposite of multiplying by the exponent? Dividing by the exponent. And what's the opposite of doing the power rule? I have to do both of those reverse things, but also in reverse order, just like the shoes and socks. Okay? So, what do I need to do here? I need to add 1 to the power, and what do I get? 1/2. And then I need to divide by that new power. Okay, now what does dividing by this 1/2 do? What's, no, it doesn't, because I'm dividing by fractions, so I have to flip and multiply, right? Because you guys all did middle school. Yeah. Do we need to send you back to elementary school? Yeah. So I actually had this really weird dream about my old middle school last night that um, they were going to decommission it, and so I was all like nostalgic because it was the last time I would ever be in that building because they were going to demolish it. But also, like, I was walking around and seeing all the different additions that they made. Like, they made it 4 stories instead of 2 and had added a bunch of different things. And, like, the cafeteria was, like, all much more awesome. And it was really weird. Um, so, and I was talking with kids that were there, and I'm like, you kids don't understand. Back when I was in this middle school, blah, 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 right? I was totally doing the old man thing. So, yeah. Um, okay, so that's what we get for y. Now, what have I forgotten here? A plus c. Okay, so there's also this unknown constant that I don't yet have determined. Okay, but I do have some extra information, namely, what happens if I plug 1 into this? What should I get? -2. All right, so -2 needs to equal natural log of 1 minus 4 square root of 1 plus my constant. All right, what's the natural log of 1? Thank you. What's the square root of 1? And so what does c need to be? 2. Okay, and so we get that. Okay? All right, now I'm going to do some graphing stuff here in a minute to kind of elucidate geometrically what we're doing. Um, okay? Um, right, so I'll give you a second, make sure you've got that good. And while you're polishing it up, I'm going to fire up Mathematica, and because I want to do some graphing. Okay, so hands on top of your head if you're ready for me to move on. Okay. Okay, we're good. All right, so let me switch the display over. Okay, and I'll put you here and you here. And then I need to do window capture, Mathematica. There. Okay, good. All right, so let me take the original differential equation that we started with, and I'm going to take the y prime equals form. So this was what? 1 over x plus 2 over square root of x. All right, and I'm going to do what's called a stream plot. Um, what do we get for our solution? Okay, so what you're looking at here is basically um, a bunch of different solutions to this differential equation. So if you pick a point on this grid, what you're doing is picking an initial condition. Okay, and the set of arrows that go through that is your particular solution. Okay, so this is a way to represent sort of all solutions, but then once you pick a specific one, then you have picked a specific one. Okay, so let me take here then what was our solution? Plus 2. Oh, other order. Oh, that's interesting. Uh, no, all the brackets are fine. Well, okay, let's go back to our solution. So, okay, this is clearly not correct because what's the problem? Well, the red line should be following the arrows, and very clearly here it is not, okay? Which means I done screwed up something, okay? So let's go back to let me make sure I didn't make any mistakes here. 1 over x plus um, 2 over square root of x. Um, okay, and then what was our solution? Log minus 4 square root of x plus 2. Okay, so what did I manage to screw up here, guys? Yeah, should it be? Oh, yeah, yeah, yeah. Okay, I'm sorry. So those should have all been positive, and so then this right here should be a plus. That looks better. Okay. So yes, okay, good. That's better. Now, all right, my graph here is maybe not particularly elucidating in this case because but is my red line following the arrows? Yes. Okay. Now you might say, wait a minute, Dr. McKinney, it doesn't exactly go on top of some arrows, but you have to think that there's really infinitely many sets of arrows between all of these. It's just I can't graph all of them because otherwise the screen would be too jumbled up. Okay. Um, okay. So yeah, good catch on the plus. So that explains that problem. Um, yeah. Okay. Good. So question preguntas fragen. Yeah. It would, because now what should C be? Minus 2. Ah, uh, yes. Okay. So C is -6. And so Yes, okay, so let's change that. And so what do we say this was, -6? There we go. Okay, now, so that's still following the arrows, okay? So if you mess up your initial condition, you still have a solution, it's just not the right one, okay? Now, in particular, what was the initial condition that was given to us? That y of 1 was supposed to equal, okay, and so geometrically on the graph, that means that my red line should go through the point 1 minus 2. Does it? Well, now it does, okay, because 1 minus 2 is right here, okay? All right, so now we've got it. Good. You want to teach class next time? No. I can sleep in. It'd be great. So, okay. Um, just for a couple of quick minutes before we finish here, we're going to start doing a little bit of physics, which is to say, what is the meaning of the first derivative and the second derivative and the original function? Okay, so in physics, what's the meaning of the original function often? Where something is. Okay, its position. Okay, what would the meaning of the derivative be? Its velocity. What's the meaning of the second derivative? The acceleration. Okay, now, if we take just sort of basic Newtonian physics, right? So if I take this pencil and I release it from my fingers, what happened? Gravity pulled it down, okay? And technically, gravity also pulled the Earth up so that the two met somewhere in the middle. Except, did the Earth move basically? No, because the Earth, like Patrick's mom, is so massive that in relation to the pin, it, yeah, I know, right? Like, I had to, right? Okay. So anyway, yeah. So like when I drop this thing, right, the moment it's released from my hands, gravity, there is a net force on the thing. Okay. And what is that force? Well, once I've released my finger. Okay. The net force is gravity pulling this thing down, and gravity, force equals mass times acceleration. What's the acceleration involved here? The negative 9.8, blah, 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 which is gravity. Okay, so negative 9.8 meters per second. And gravity for, the distances involved with my pin and the floor, we can treat as being a constant value. Okay, it's not really constant. Gravity is slightly stronger at the floor than it is up here, but is it like really that much stronger? No. Okay, so we can treat gravity as being a constant for this purpose. And yeah, so our second derivative will be constant, namely equal to gravity. Okay, in many of these physics problems. Okay, and we'll polish up with that first thing on Friday. Last piece of business. Next assessment Monday. Okay, not Friday. Sound good? All right. See you guys later.